Hi, we're running openwsn using 50 nodes topology. As you can see, all the nodes are sort of connected. And it has been over a couple of hours since this topology has been in the shape. So most nodes are hardly at 4 hops away from the main router. And these are the nodes, as you can see. Now we're going back to our simulation, which has been running for over a couple of hours. In here, we see packets, big packets are being divided into fragments, and each fragment is sort of measured 90 bytes or 89 bytes. DAOs sent regularly over the time by the modes to the root, and this helps update the path and the location of the mode. Now, scheduling, as you can see, 6 top, return 3, 7, 9, these all are scheduling states. We'll explain that in another video sometimes, how this works, but at the moment we're only going to show how WSN is running using the old repository. So using the scon command. Now we're looking at the routing. So the routing table shows the routes available here to the nodes. And the rest would be here. You look at the output. So in the output, we received 2 log files, and these files have the most of the data in there. So the first one's a packet info log, which contains the log. Here, latency is recorded per packet, and counter is basically is 1 packet. So if you're looking at 00 something here and a source ID 0014 or 003 or 002D, then it has a counter too, which will increase only in the next iteration of the source ID. So that means number of packets being sort of received, and TX number of TX cells being used by the mode, and ASN, which is a time. To convert this ASN, there's a very simple formula, and that is to multiply the value by 0.02 and divide it by 60 to get it in the minutes. So you will get time in the minutes, and then you can sort of plot it. You can also plot it over slot frame cycle. So after every 101 slots, there's a new cycle. So you can also do that. Under the duty cycles, it shows that the out of the given proportion of the slot duration, how much and how long did it take to complete the task. So each TX or RX, how long did that take to finish the task. So that's the duty life cycle for that. Reception takes fairly smaller value, whereas the transmission takes consume most of the current. So this is one file, read only just now. We're going back to another log, which we have received once we started our UDP application on top of openwsn stack. So yeah, it shows the PDR, shows the average cells uses, and it shows the latency, average latency. So average is the data. Now, this is one thing. We need to just look at the aspects of what triggers these packets and how frequent these packets are running. So we're going to inject under firmware, under applications, and here we've got the inject. So this C file, to give you a quick demo to it. So this basically prepares a UDP packet and dispatches it as a payload. And then when the payload is received, it sort of extracts the data and parse it into sort of acceptable formats. The parse the bytes basically. So here we see that the traffic rate, the number of packets, 2, and we're going to see the value per x minutes. So the x minute is in .h file here. So it was 60 seconds, but now we put it half, so it's 30 seconds for now, which means in 30 seconds we're dispatching 2 packets, and most likely I would say they're 4 fragments in 30 seconds. So, and this is how, so it will sort of continue over time and in an endless manner. So yeah, this is just a quick experiment. You also can capture the results using the uinject Python file, which sort of captures the state of mode and plot it in the once the application comes to the end. So here slot duration is 0.002, and that's what we also thought, but we have changed the slot duration, which I believe was 0.015. Yep, going back, another application we have is the uecho. So this normally sort of, right, UDP echoes, it toggle the nodes basically. There are different types of applications available in the application folder, which monitors the state of node. Now, there are many other ways you could look into the neighbor modes, further states, which are about the neighbors, about the quality of links, and about the scheduling part. So there are other ways that you can plot these, and most likely it will be through so basically the data is being sent to OpenVisualizer, as you can see on the OpenVisualizer, and from OpenVisualizer you capture the state into event logger, and in event logger you can uncomment this file to get the rest of the data. Basically about the mode states, I mean the probing modes and more deeper. Okay, so here we are. For debugging purpose, we also sort of have an OpenVisualizer log file. Now this file basically, so as I was showing you, so it's showing today's stage. So the simulations sort of started today at about this time, and then it kept on running. This basically is the data. It's continuously running since then, so it's quite a heavy file. So yeah, and what is injecting in there is also shown the 6-loop packet, source root, you know, the other bits of information, address of source and the root, the destination node, payload, bytes. So it's all being recorded here. So this file is useful for debugging purpose, and that's what we use for debugging. In our paper, we have shown that the status of the queue, how well it utilized, because it throws the errors if there's sufficient space there. So this is currently what we have this year. So DAO sequences, as you see, that's what the DAO's been sent, and is pretty much well sequenced. For more, you can see the flow diagram on Wireshark, so you can capture more through there. Okay, so I think that's pretty much all for today. Thank you for watching.